What if the force that holds you to your chair is the same force that bends light and warps the very fabric of time? In 1905, Albert Einstein changed physics forever with his theory of special relativity. Yet, even as the world grappled with his masterpiece, he knew it was incomplete. He was deeply unsatisfied. What was the missing piece? In the midst of the turbulent times of the First World War, as nations were locked in conflict, Einstein was engaged in one of the greatest intellectual achievements in history. As one physicist described it, his work was a lighthouse in human history, a testament to what the human mind can achieve even in the darkest of times. While his earlier theory of special relativity was, in a sense, in the air, an idea whose time had come, built on the work of many colleagues, the theory he was now creating was different. General relativity was almost an entirely original leap of imagination. Einstein's core problem was a deep dissatisfaction with his own work. Special relativity described the universe for observers moving at a constant speed, but it had nothing to say about acceleration or, crucially, about the universal force of gravity. This omission gnawed at him, setting him on a decade-long quest to solve the mystery. The key that unlocked the universe for Einstein was a single, profound insight he called his happiest thought. As legend has it, the idea came to him while observing a window washer working on a nearby roof, imagining what would happen if the man were to fall. This led to a simple thought experiment that forms the conceptual foundation for all of general relativity, the equivalence principle. Let's imagine you are standing in a completely sealed room, a box with no windows and no connection to the outside world. First, picture this box resting on the surface of the earth. You stand on the floor and feel your own weight, a familiar downward pull. Now, let's transport that same sealed box to the emptiness of deep space, far from any planet or star. The box is attached to a powerful rocket that begins accelerating upwards at a constant rate of 9.8 meters per second squared, the exact same acceleration as gravity on Earth. Einstein's profound realization was this. Inside the box, the feeling would be identical. Your feet would press against the floor with the same force. If you dropped a ball, it would fall to the floor in the same way. There is absolutely no experiment you could perform inside that sealed room to tell the difference between being stationary in a gravitational field and being accelerated in empty space. This works because an object's inertial mass, its resistance to being accelerated, is precisely equivalent to its gravitational mass, its response to a gravitational field. In other words, gravity and acceleration are two sides of the same coin. This simple but powerful idea was the key that unlocked the rest of his theory. But if gravity and acceleration are fundamentally the same, what does this imply for something that is supposed to always travel in a straight line, like a beam of light? Einstein's equivalence principle leads to a stunning and radical conclusion. Space and time are not the static, unchanging backdrop we imagine them to be. Instead, they form a dynamic, flexible fabric that can be bent and warped. To understand how, let's return to our thought experiment. Imagine you are inside that accelerating rocket ship. You take out a laser and shine a beam of light from one side of the room to the other. From the perspective of someone watching from the outside, the light beam travels in a perfectly straight line. But because the rocket's floor is moving upwards at an ever-increasing speed due to its constant acceleration, the beam will strike the opposite wall at a point slightly lower than where it started. To you, the person inside the rocket, the path of light has visibly curved downwards. Now, we must apply the equivalence principle. And if a light beam curves in an accelerating reference frame, it must also curve in a gravitational field. This led Einstein to his greatest insight. Light always takes the shortest path between 2 points. So if we see its path bend, it doesn't mean the light is curving through straight space. It means the light is following a straight path through curved space. He realized that massive objects don't create a mysterious pulling force, as Newton had thought. Instead, they warp the very geometry of the universe around them. But why is it called spacetime? Because you can't curve space without also distorting time. Think back to Einstein's first theory. The speed of light must be constant for all observers. Now consider the simple equation. Speed equals distance divided by time. If a beam of light travels through a gravitational field, its path is now curved. This curved path is a longer distance. Since the speed of light cannot change, the only thing that can compensate for the longer distance is time. Therefore, time itself must pass more slowly in a gravitational field. Space and time are woven together into a single four-dimensional fabric. A common analogy is placing a heavy bowling ball onto a stretched trampoline. The ball creates a dip, and a marble rolled nearby will follow the curve created by the ball. This was a theory of breathtaking beauty and scope, but to be accepted, it had to make predictions that could be tested in the real world. A scientific theory, no matter how elegant, is only as good as the evidence supporting it. General relativity made several extraordinary predictions that were unlike anything seen before. These crucial observations transformed it from a wild idea into a cornerstone of modern physics. 1. Mercury's strange wobble. For decades, astronomers had been puzzled by the orbit of Mercury. Its elliptical path around the sun wasn't stable. The entire ellipse slowly rotated over time, a phenomenon known as precession. Newton's laws of gravity could not fully account for this strange wobble. When Einstein applied the equations of his new theory to the problem, they predicted the exact amount of precession that had been observed for decades. You can only imagine how Einstein felt. For a moment, he was the only person in the world who understood how the universe truly worked. 2. Bending starlight. The most dramatic proof came in 1919. A team led by English astronomer Sir Atherton Eddington traveled to observe a total solar eclipse. Their objective was to photograph the stars located near the sun's edge. According to Einstein's theory, the sun's immense mass should bend space-time enough to deflect the starlight passing by it, making the stars appear to be in slightly different positions in the sky. When the photographic plates were analyzed, that's exactly what they found. The stars had shifted by the precise amount Einstein had predicted. This confirmation made Albert Einstein an overnight global celebrity. 3. Modern verification in a digital age. Today, general relativity is tested constantly with incredible precision. The Shapiro effect demonstrates this beautifully. When scientists send radar signals to Venus, the signals are slightly delayed when they pass near the sun because they're traveling through the dip in space-time created by its mass. GPS technology relies on general relativity to function. The satellites orbiting Earth are in a weaker gravitational field, so their internal clocks tick a fraction of a second faster than ours. If GPS systems didn't constantly correct for this, your map would be inaccurate by several kilometers every single day. And perhaps most stunningly, when lasers are bounced off mirrors left on the moon by Apollo astronauts to measure its orbit, the calculations are so precise they must account not just for the mass of the Earth and Moon, but for the mass equivalent energy of their combined gravitational field, an effect predicted only by general relativity. General relativity doesn't just describe the gentle orbits of planets, it also predicts some of the most mind-bending and extreme phenomena in the cosmos. These aren't just theoretical curiosities, they're real objects that reveal the universe's strangest secrets. A black hole is what happens when gravity wins the ultimate battle. It is a place where matter has collapsed under its own gravity so completely that the curvature of space-time becomes essentially infinite. The gravitational pull is so immense that the escape velocity exceeds the speed of light. Because nothing can travel faster than light, anything that crosses the boundary of a black hole, known as the event horizon, can never escape. All of the complex matter that falls in, protons, electrons, entire stars, is thought to be ground into a uniform mush. Imagine an astronaut falling toward one, sending a signal back to you every hour. As they approach the event horizon, the signals, sent every hour from the astronaut's perspective, would arrive at your telescope further and further apart. The 1 hour interval was stretched to 2 hours, then days, then years, until the next signal is effectively delayed until the end of time. Thankfully, our sun will never become a black hole. Only stars 20 to 30 times more massive can end their lives this way. The nearest known black hole is a safe 1,500 light years away. Since gravity bends light, any massive object in the universe, an entire galaxy, a cluster of galaxies, or even a huge invisible clump of dark matter, can act like a giant cosmic lens. As light from a very distant galaxy travels towards us, its path can be bent and magnified by the gravity of a massive object in the foreground. This leads to some of the most bizarre and beautiful mirages in the cosmos, such as multiple images of the same distant galaxy or smeared out arcs of light. In cases of perfect alignment, it can even create a complete circle of light, known as an Einstein ring. At Cosmic Origins Revealed, we find this fascinating because gravitational lensing allows astronomers to map the location of dark matter we can't see directly, simply by observing how its gravity bends the light from things we can see. It's like the old joke of the drunk man searching for his keys under a streetlight. Not because that's where he lost them, but because it's the only place with any light. For astronomers, the light from distant galaxies is our streetlight, illuminating the invisible structures of the cosmos. General relativity stands as one of the greatest achievements of the human mind, but it is not the final word. Its very success points toward an even deeper mystery at the heart of physics. The fundamental conflict is this. General relativity is a classical theory that magnificently describes the universe on the largest of scales, planets, stars, and galaxies, but it is fundamentally incompatible with our other great pillar of modern physics, quantum mechanics, which describes the universe on the smallest subatomic scales. This conflict comes to a head inside a black hole. General relativity predicts a singularity at the center, a point of infinite density where the laws of physics break down. In science, infinities are usually a signal that a theory is incomplete. The grand goal of modern physics is to resolve this conflict by finding a unified theory of quantum gravity. Such a theory would merge relativity and quantum mechanics into a single, deeper framework capable of describing the two most mysterious places in the cosmos, the heart of a black hole and the very beginning of the universe at the Big Bang. Einstein's theory gave us the universe as we know it, a cosmos of curved space-time and incredible vistas. But his true legacy is the journey he began, the search for the single, elegant set of laws that governs all of reality. The final answers are still out there, waiting to be discovered. We've traveled from Einstein's profound dissatisfaction with his own theory through his happiest thought to a modern universe filled with warped space-time, black holes, and cosmic lenses that reveal the invisible. His idea truly rewrote the rules of reality. If you were fascinated by this journey through Einstein's universe, Be sure to subscribe to Cosmic Organs Revealed and hit the like button. Share this video with anyone who loves to wonder about the cosmos. And let us know in the comments, what part of general relativity blows your mind the most? Thanks for watching.